All right, let's talk about one of the most fundamental data structures out there, the tree.
So you're probably used to linear data, right? Well, trees are different. They're all about hierarchy. Think of it like a family tree. It's just a bunch of nodes connected by parent-child relationships. And every single tree kicks off with a special node called the root. It's the only one without a parent. Now here's the cool part. Every other node has exactly one parent, but it can have tons of children. And those nodes at the very end of a branch, the ones with no kids, we call them leaves. So a node's depth is basically how far it is from the root. You can just think of it as its level. And height? Well, that's kind of the opposite. It's the longest path down from a node to a leaf.
Okay, so how do we actually visit every single node in a planned way? That's called traversal.
With pre-order traversal, it's simple. Visit the parent first, then its children from left to right.
And post-order? You guessed it, it's the reverse. We hit all the children first, then the parent. Now let's zoom in on a super common type, the binary tree. Each node has two children, tops. This gets to a classic problem. Arrays are fast to read but slow to update. Can we do better?
Absolutely. Enter the binary search tree. It's a binary tree specifically designed for super fast searching.
And here's the magic rule that makes it all work. For any node, left is less, right is more.
This rule is a total game changer. You get to chop your search in half with every single step.
So what does that mean for performance? Well, search, insert, and delete all depend on the tree's height, h. In a perfect world with a balanced tree, that height is about log n. And trust me, that's crazy fast.
But what happens if the data is sorted? The tree just becomes a long chain, kind of like a linked list.
Which leaves us with one big question. How do we keep that tree balanced and lightning fast as it grows?